16 partially. Probably we'll do session 1. Yeah, we'll just do session 1. Session 1 and 2, so that we know the definition of acid base. Okay, so let's talk a little bit about. Okay, yeah, session 1 and 2. So we will end in here, question 19, 20, right, partially. All right, let's get started. Session 16.1, we got to talk about acid and base. So far, we have two different definitions that you need to know. Arrhenius and Brown-Larry. We also talk about Lewis, but Lewis is no longer on the AP exam, so we'll focus on Arrhenius. Kind of. So Arrhenius, what Arrhenius did was basically what we've been talking about acid base a little bit ago. Remember I said when we talk about acid, they have what in there? H, right? And then when we talk about base, what did they have? OH, right? So same idea here. So you have acid are basically substance that increase concentration of H plus. Okay, we're good with the bracket, right? Concentration of H plus when dissolved in water, H2O. Yeah.
Wait, so when an acid is eating something, is it kind of just reacting with it?
Yeah, basically, it's reacting with it by giving away the H plus. Oh. Yeah. Base is the substance that increase concentration of OH, right? Minus when dissolved in water. Okay, so what does that mean? That means Arrhenius solution is very limited because they have to be dissolved in water, right? Because they keep saying this. So Arrhenius solution is limited to aqueous solution, right? Okay, we all know what aqueous solution is,
Yeah.
right?
Are there any solid acids that can like eat stuff while solid?
By definition, you could, but not by the Arrhenius equation. So there are different acid-base equation that we have. So,
well, yeah, this is what I'm talking about when I say maturity.
all right. So by definition, when we're gonna say by Arrhenius, no. Arrhenius is only talk about aqueous solution. All right, let's go through number 3. You need to write down a dissociation of each of these in an aqueous ion form. So HCl is gonna do what? Right, it's gonna go H plus and Cl minus. Okay, what's their state of matter? Aqueous. Right? AQ, AQ. Okay, now how about NaOH? Right, it's gonna be Na plus AQ plus OH minus AQ. Notice, don't break the O and H apart. Okay, hydrochloric acid. You guys know who is it? That's literally HCl again, right? Okay, so you know we already wrote it up there. Okay, tricky. Acetic acid.
Vinegar. It's like CH blah blah something.
It's come from acetate. You guys remember what acetate is?
Like
H3.
COOH.
Yes. CH3COH. Okay. So it's gonna break apart. So it's gonna have, again, it's acid, so H plus is gonna go away, right? It's gonna be AQ. And then you're gonna have CH3COO minus. And then that's also AQ. Okay, one thing I want you guys to know, I know we haven't talked about it yet, but acetic acid is a very weak acid. Therefore, we're gonna draw the double arrow on this one. I'll explain you later in the session why it's a double arrow, but I just want to say that. We'll get to that.
Yeah, weak acid.
I think I did talk about it. You guys remember strong acid, weak acids?
Yeah, it just means it doesn't fully dissociate.
Right, there you go. Yes. Hey, remember from back then. All right. Brown-Larry acids and base definition. So what is Brown-Larry talk about? Brown-Larry talk about is he talk about transfer of H plus ion from one substance to another. So this guy focuses on the H plus. Okay. Now H plus ion, this is another way to write H plus ion, is also H3O plus. Sometimes you will see that is also, yep, it's called hydronium. Okay, hydronium ion. So sometimes they will write it as H3O plus. It's the same thing. So let's talk about Lewis dot structure for both water and hydronium. So how did water look like? Right, H2O, right? O with a 2H. We know it's bent, so I'm going to draw it like bent. And then we're going to have 2 lone pair. Right. How would hydronium look like? Well, first of all, it's going to have 3 H's. So probably something look like that. Okay, and also don't forget that it is a plus. So I do need to write the bracket like this. And I'm going to need to write the plus on the outside. Okay. And you got to think about what happening. How many electron total this guy has? I haven't finished yet. Hydronium ion. That is a lone pair? Just one lone pair.
Just one pair.
Make sense? Yeah? Guess what? These two has the same number of electron total. You guys know this? Yeah?
Oh,
Yeah, they have the same number, right? They are isoelectric. They have the same number of electron, right? This one, even though it has one more extra H, is the plus ion. So it has the same number of electron. All right. Okay, so chemists use the symbol H plus and H3O plus interchangeably. So when referring to iron, right, to determine acidity or solution, so you might see both H plus and H3O plus. They are the same thing. We're gonna say that they are the same thing, okay? So when you hear H plus iron, okay, okay, so when you hear H plus iron, you're gonna refer to as a, yes. You're not gonna get yourself confused in college. Yes, H plus is a proton because remember what we talked about. Hydrogen only has protons and electron. So when you become plus, what does that mean? You lost an electron, so you only have protons. Okay, that was the question that I got asked before. Yes,
I'll put a neutron onto a hydrogen
you could, but that would be a rare species of hydrogen atom, right? Because hydrogen atom has 3 isotopes. The most common form is the isotope without a neutron. Okay, let's talk about 5A. Write the formula for 2 products that form in this chemical reaction. So what is this gonna form? So HCl and NaOH, right? I mean, H2O. Oh my goodness. HCl and H2O. We said HCl is acid. We know it's about it before. And we said based on Brownstein-Larry, it's gonna remove H plus. So H plus is gonna fall out of HCl and it's gonna go glued to the H2O, right? So what's gonna happen is you're gonna have Cl minus, because it's aqueous, and then you're gonna have H3O plus, and that's gonna be aqueous. Nope, not liquid. Okay, so now what's happened? HCl, as we know, is behave as an acid. Okay, you got to remember that one. Is acid because it's donate. H plus, and water here behave as a base because it's accept an H plus, right? So if you donate an H, you're H plus, you're the acid. If you accept the H plus, you're the base. Okay, Brownstein-Larry definition of acid and base. Does it require reaction takes place in aqueous solution? The answer is no. Okay, is only need transfer of H plus ion. Okay, as long as H plus is moved from one to another, you have an acid and base. Okay, number 7. Acid-base chemistry can occur in the gas phases. Okay, in this case, 2 gas react together to form a solid ammonium chloride. Identify acid and base in this equation. Well, It's already said ammonium chloride is produced, so let's write it down. What is what is ammonium chloride? NH4Cl, right? NH4Cl. So that's a solid. So let's talk about it here. What is happening in that case? Is right, this H is gonna go to this guy, right? NH3 accepted an H. So NH3 is a base, and then HCl is a acid, right? It's give away its H. Okay. 8A, write a formula for two things that's just gonna produce. Oh, why did I? Okay, 8A, 8 is already said. I don't know why I said it twice. Okay. Oh no, it's not. It's a different one. Okay. So what? Oh, I see what it is. Okay, what happening? Okay, so you have NH3 and an H2O. This is gonna be strange. You should know that NH3, we talk about it. This is a base. Ammonia is a base. We heard about it. It's right? Yeah? It's a base. So what's that gonna happen? That means H from here is gonna go and give it to this guy. So you're gonna have NH4 plus, and then you're gonna have OH minus. So you're gonna form ammonium hydroxide basically. That's AQ. That's the AQ. So identify the acid. H2O behave as acid. Water is very weird. And NH3 behave as base. Okay, now 9. By definition, define Bronsted-Lowry acid and base. Now that we've been talking about it for a long time, what does Bronsted-Lowry acid do? Right, it's gonna give off proton, right? So Bronsted-Lowry acid will donate H plus, the protons. Okay, you can say protons. Okay, positive ion, right? Bronsted-Lowry base will accept proton. Okay, or H plus, we said. Besides that, you also need to know something peculiar about Bronsted-Lowry base. Bronsted-Lowry base has a lone pair electron. That's why it's accepting the proton is easy, right? Because it doesn't have extra electron. Why would they take a plus, right? So base also have a lone pair, at least one lone pair or electron. Okay. All right. Okay. Every acid has a conjugate base. I don't know if I talked about that one before. Conjugate base and conjugate acid. So acid will have conjugate base. What does that mean? Conjugate base is gonna form by removing a protons from the acid. And then when a base accepts a protons, it become conjugate acid. Okay, conjugate. All right, so the next one, we're just gonna define these as acid base, conjugate acid, conjugate base. So you're gonna say acid base. I'm just gonna shortcut it. I'm just gonna say AB, and then that would be Ca, and then that would be a Cb. Okay, so let's talk about it. So which one is acid, which one is base? So let's find out what happened into the hydrogen. So who get hydrogen and who lost it? H2O is accepting, right? So this guy loses to this guy. So since this guy is giving, this is called acid, and then this is base. And then so NO2 minus is from HNO2, so that means this is a conjugate base, because acid conjugate base, so therefore this is a conjugate acid. Make sense? All right, let's try that another one. All right, you guys are funny. Okay, so what happening on the B? Who is giving a protons? Water is given protons. This way. So who's the acid? NH2 is the acid?
No base.
Base. Okay. Because it's except what? This is acid. Okay, so what is NH4 plus? Base. Acid. Because remember, a pair, right? Base, conjugate acid, acid, conjugate base. Okay. All right. Notice something fishy about A and B? Look at water.
It's a base and an acid.
Ah, water can behave like both base and acid.
Why is water so weird?
In fact, it's not just water. There's a couple of things that can do that. So that's lead to the next one called MP floated. MP floated is basically a substance that can act as either base or acid, depends on the substance they interact with. Okay. So in D, we said who is an example amphiphlogic substance that you already know now?
Water.
Water. Okay. Make sense? All right. So let's go to the. Oh, yeah, you guys are still writing. Let's go to the next page. I want you guys to go ahead and write your conjugate acid and base. Go ahead and try them to see if you guys can write conjugate acid and base. Notice that to write conjugate base, what are you simply doing from this? Acid. So what did acid do? Remove the H, right? So if you remove the H plus, what are we gonna get here? That's what you're doing. Yeah, so that's what you're doing. F minus, and then do the rest. And then you're gonna do the conjugate acid too. Okay, don't look. So I want you guys to try without it. Just lose one. Just lose one each. Yeah. And then on the side, you're gonna do base to the acid, conjugate acids. Same thing, just only gain one H.
Where do you put the H on the CH3H?
It's on the N. Good question. Okay, done. When you finish, go ahead and go to the check the answer, and then go to the B, and then do the MP fruitage. So look for a substance that can act like both acid or base. So acid or base.
Oh, wait. It's in both tables.
Pretty much.
Oh, okay.
All right. So who are the MP fruitage?
H2O.
H2O. That's it.
HCl3.
Mm-hmm.
And HCl4.
Mm-hmm. That's it. Yeah? Because they both, all these three can act like either acid or base. Now notice that we don't know who they're reacting with. It's depending on who they react with. They could do either. Okay. Let's try to an example. So let's try writing an equation for one HCO3 minus 1 might behave as acid and one is gonna behave as base. So we're gonna react with water to see how it's gonna look like. Okay. So let's try. So HCO3 minus 1 plus H2O. How's that gonna look like? So remember we said it wants to behave as an acid. So how would that look like when it's trying to behave as an acid? Right. So you're gonna have H3O plus, and then you're gonna do CO3 minus 2, right? Because it's gonna lose it, right? And then now we're gonna try to do it so that it's behave as a base. So how would that look like? Oopsie. So you're gonna do, I heard it, H2CO3 and then OH minus. All right. Now, if you don't want to do -1 or +1, you just do plus minus. That's fine. As long as it's legible and they can read it, you will get a credit. Because otherwise, you can just say +1. I usually don't write 1, so it's just a habit. All right. Okay. So number 14, you gotta explain the relative strength of an acid and conjugate base, and then conjugate base, and conjugate acid and base. So what does that mean? Okay, so that means the stronger the acid is, the weaker conjugate base. Okay. Same thing go for the base, the stronger base. The weaker conjugate acid. Okay. I need you guys to explain this one. Number 15, you already know. We talked about it before. What is the difference between the strength of the strong acid versus a weak acid? How do they behave? Dissociate, right? Strong acid will dissociate more than the weaker acid, right? In fact, the strong acid will dissociate completely. That's why we draw with one arrow, and a weak acid we draw with a 2 arrow, right? Because it doesn't dissociate the whole thing. Okay, so strong acids will dissociate completely. Okay, or you can say dissociate more. So for example, you can see HCl is gonna make H plus and then Cl minus, right? AQ solid. Okay, whether weak acids will not dissociate completely. I think I'm spelling error today now. All right, so what does a weak acid look like? We just have one earlier, CH3COOH, right? Even if it's liquid, it's gonna dissociate this way, CH3COO minus, and then H plus, and then this is AQ. Now notice that I need the return arrow back because it doesn't dissociate completely. As it's dissociate, they're gonna go back and phone it back again, so they didn't. Okay, I need you to memorize the number 16. Okay, number 16, you need to memorize this because those 7 are the strong acid, meaning they will dissociate completely. Okay, and then the rest are the weak acid. Okay, so I'm gonna let you guys write down the formula for these two as a review because you should know how to write these. Yes, try them. You kind of forgot. If you forgot, you can use your periodic table, like the old one that we used to have. If you forgot how to write some of them, but yes, you should know how to write them. Okay, let's try writing them. So what is hydrochloric? Okay, you want to write all this basically. Okay, got it. Okay, so I want you guys to use your tables. Let's try writing it. All the names. You hear you? There's the next one.
Wow. Ủa? Cái đầu tiên
Yes. Part of it. It's come from benzoate. Okay, more or less, this is what it is. I'm just gonna draw the benzoate so that you guys can kind of like see it. It's also known as this. I would say, actually, I'll just draw it. It's something like that. That's where it is happening. It's a benzoic acid. It's a benzene ring with the carboxylic acid, basically. Yeah. So benzoic acid. This H is the one that is coming out, falling out. Okay. Okay, so let's talk about a couple other things. Finish? Yeah. Nitrate acid. Iron. Nitrate iron has a negligible basicity, meaning we're telling you that nitrate iron is somewhat basic. Why?
Oh, because it's a strong acid.
Right, it's coming from the strong acid, so that's why it's negligible. Negligible is a very small amount, right? Because nitrate, right, NO3 minus 1 is conjugate base of strong acid. Okay, remember, strong acid dissociate completely, making the ions, right, or the in this case conjugate base, right, close to neutral, meaning they're not gonna to behave like a base and go grab the H back. Okay, because NH3 don't want the H. So they're not gonna grab it back to make NH3. Not gonna happen. Okay. Why is fluoride iron classified as stronger base than chloride iron? Okay. Why is F minus 1 is more basic than Cl minus 1? Yes, it's basic. Right. Right. Because HF is a weak acid and HCl is a strong acid. And then and then on the AP, if they keep asking, you can add a little bit about dissociation. Okay, dissociation different is gonna make it so that F minus really want that H. F minus is more attracted to the H than a Cl minus. Okay. All right, let's see. Let's take a look at the last question of the day. Number 20. Take a look at this thing. You have this graph. This graph will be given to you if you need to compare the strain of the acid base stuff. If not, all you need to do is you need to remember those seven. Those seven are permanently the strong one. Anything else that they give you is a weak acid. Sound good? Okay. So used to be people remember both acid and acid, weak and strong, and acid is too much work. Okay. So what we're gonna do is we're gonna write little a for the weak acid and then capital A for strong acid. So we're gonna compare them. So let's take a look at this. So we have an interaction. We gotta figure out which one is the stronger one. We have HSO4 minus 1, right? This become this. So that means this guy is giving a H to this guy. Agree? Yeah? Whether in here, this H is being given to this guys. See that? So meaning in both sides, you see that HSO4 minus versus HCO3 minus. Who is a stronger acid? Let's take a look. Look in your table. HSO4 minus versus HCO3 minus. Okay. I see HCO3 minus here. HSO4 minus. Where does this go? Right here. Do you see that? So HSO4 minus is a stronger acid because acid strength increases this way. This is a stronger acid. This is a weaker acid. Agree? And then you're gonna look for the you have your tables. You're gonna look for that. So you're gonna look between these two. Who is the weaker base? So you're gonna compare on this side for the base. So SO4 right there. That's a SO4. And then CO3 right there. So SO4 is a stronger, weaker base. Right, base kind of go this way. So this is a stronger base. This is a weaker base. See how it's go? That means which arrow is this gonna favor? Okay, these are strong. These are weak. So which side is gonna favor? The weak side, because strong one would dissociate, right? So they said they're gonna give away or taking whatever. They're gonna do what they're gonna do. These guys are not gonna be as efficient at their job. Think about like those bucket one with the water. They are trying to give and take, right? So one of them has a bigger cups, the other one has a tinier cups, right? So that's what it is. So this is gonna be more stronger than this. So this is gonna to happen, right? This forward is gonna to favor more, so to speak. Right? So that means equilibrium is going to lie to the right side because you're going to have more of the right side. Right? So that means your K will be greater than 1 or less than 1. Greater than 1. Okay? Meaning you will have more of this lying around. Got it? How to do this? Yeah, so you're going to continue to do the other 4. And then I want you to write down this. Okay? That's it. Make sense? Yeah? Okay, let's go. So let's go ahead and figure out those. Don't look. So let's see. Yeah, I know it's a little light to tell, but yes, I know it's a little too light.
Wow, they're gonna have fun with this video.
Hmm?
They're gonna have fun watching this video.
Yeah. What happened? Let's go, guys. Come on. Let's figure out who is taking what in a sense. I know. It's really hard for me to read it too. Okay, we got it? No? Wait. Come on. Let's figure out who's the stronger acids and who's the stronger base. It's important that you can tell who's acid and base too. So first step in telling I, it,
Why do they write vinegar two different ways?
they do that sometimes, yeah.
Consistency, please. Can I get a little consistency up in here?
Well, now you see the different way that they wrote.
Problem.
Okay, so you kind of should have this chart. Yeah, AABB stuff.
I can't even find a lot.
So
Literally on
yeah. Okay. I can see that, yeah, the majority complain on over the acetic acid. Yes, they can be writing in multiple way. The most usual way that they will write is they will say CH3COOH. Sometimes they write the H in the front and then they might say HCH3COO. Sometimes they combine everything together and then they might say C2H3 O2H, or sometimes that H is in the front. Yes, so they do write it as a multiple different way, but those are all acetic acids. I know it's super strange way of writing, but I see all kind of way before. So as far as equilibrium lining, if you for the strong acid, right? So equilibrium is gonna lie far to the, well, if you have a strong acid as a reactant, equilibrium is gonna lie far to the right side, the conjugate side, right? Which mean the constant K is gonna to be greater than 1, okay? Okay, but if you start with a weak acid as your reactant, then equilibrium gonna lie farther to the left side because it's still gonna stay around that weak acid, and your K is gonna to be less than 1. You're not gonna dissociate as much, which makes sense if you think about it, right? Dissociation. Make sense? Okay, so pretty much I'm gonna stop my recording at this point.